So let's recap summing a geometric sequence. This can serve as an intro if you've never seen it, but might be a little cryptic at the start. Here's what we discovered in class, or some of the things we discovered in class. These very suggestive examples that when you take 1 plus 2 plus 4 plus 8, this summing the powers of 2, you get the next power of 2 minus 1. So if you go up through 2n to the n minus 1, like through 16, for example, you get the next power of 2, which would be 32 minus 1. That's really the heart of the whole thing. This example encapsulates the basic, interesting fact. But it doesn't encapsulate everything. The next example we did was if you take 2 plus 2 times 3, 6, plus 2 times 9, 18, and you look at double the powers of 3 and add those up, you get something very similar and very simple, 3 to the n minus 1. If you take triple the powers of 4 and add all those up, you get 4 to the n minus 1. So we want to generalize that. This is clearly something interesting about very special geometric sequences, but we want to generalize it. Well, first, let me do something that's a little more algebraic than what we did in class, although for some classes I did more or less of this. Let's just put the letters in here. The usual letter for the common ratio of a geometric sequence is r. So for example, I'm not going to put in the 2's or the 3's here, but let me just put in the geometric sequence here. That's 1 plus r squared plus r cubed plus dot 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 plus r to the n minus 1. Okay, that's the basic idea, and that's exactly what we're doing in this example with r equals 2. But then what we're doing is we're multiplying that by a common factor of r minus 1. So somehow the really pretty examples and the pretty punchline that's coming out seems to work exactly when there's a common factor here that's equal to 1 less than the ratio, the common ratio, or sometimes I call it the multiplier. Okay. Now let me just do this. This is very much the heart of the standard algebraic proof of the sum of a geometric series. Let me just FOIL that out. Now that we've got to guess that it's a good thing to do, and I think that's the least obvious part of the usual proof. Is like, why would you do this? We just saw this come out of some numerical investigations. Once you've got this guess that this might be simple, then you can just FOIL it. So we're going to get r times 1 is r, plus r times r is r squared, plus r times r cubed is r times r squared is r cubed, plus r to the 4th, and I think we're getting the idea, plus, okay, and then all the way up to r to the n, okay. But that's just the r times all this stuff. Now I'm going to subtract 1 times 1 is 1, and then also 1 times r is r, and r squared, and r cubed, and r to the 4th, dot dot dot. And where does it stop? It stops with an r to the n minus 1. Now I want to emphasize something. There is an r to the n minus 2 hiding in here in the original pattern, which we didn't really have to put in because it was pretty obvious that it was there, but that helps us right here realize, oh, that r times r to the n minus 2, let me just fill in one more of those dot dot dots, that's going to be an r to the n minus 1 here. And that's useful because that makes it clearer the pattern of cancellations that we get now. We get some massive cancellations here. R minus r cancels, r squared minus r squared, r cubed minus r cubed, r to the n minus 1 minus r to the n minus 1. Wow, it almost all cancels. What doesn't cancel? The only thing that doesn't cancel on the top is the r to the n, because that was, to get that high a power, you had to have the r times this very highest power here. What doesn't cancel on the bottom is the minus 1. All of these guys were at least r to the 1. This guy is left out. And voila, r to the n minus 1. Okay, so this is exactly a generalization of these three examples with r. This is the example with r equals 2, 3, and 4. And so indeed, it wasn't an accident. It wasn't special to these three numbers. It's a general phenomenon. Okay, so now what can I make of that? Well, what I really want to get is a sum of an arbitrary geometric series, geometric summation. Series is usually the name when we try to make this an infinite sum, which is going to be an interesting idea later, where it can start with any number, not just 1, and not just r minus 1. This started with 2 minus 1, this started with 3 minus 1, this started with 4 minus 1. So first, let's just isolate this part. That's easy to do. I'm just going to take this equation, this equals this, and divide both sides by r minus 1. 1 plus r squared plus dot 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 plus r to the n minus 1 equals r to the n minus 1 over r minus 1. Notice the minus 1 is outside. There's 3 places where minus 1s show up. Here on the left-hand side, the terms we're summing up, it's in the exponent. Here on the numerator, you do take r to the n, but just to the n, and then outside you subtract 1. That's this key observation that you don't quite get to the next power of the r. And then you divide by r minus 1 to get it down to this more basic case where it's really just starting with 1. Okay. Now what the heck? We're almost there, but this is still special. It insists that we start with 1. An arbitrary geometric series starts with anything a1 plus a1 times r plus, I don't need that power, a1 r squared plus dot dot dot. Okay. But that's not that much more complicated. That is just a1 times the quantity of what we just did. I'm going to copy and paste it to sort of emphasize that that's really something we just did. Oh, okay. Well, we don't know the formula for that. Okay. And so there, and let me just bring that back down too. So there's the formula, the master formula for the sum of geometric series. Okay. We use that in a similar way to the sum of an arithmetic series. We maybe have like 100 terms we have to add up here. That's a huge pain to do by hand, and also we can't sort of get patterns and formulas and further interesting conclusions out of it. This is much simpler. The n only appears in one place. It's like 3 or 4 arithmetic operations instead of hundreds over here. So let me just express it one more way. Use the summation symbol. Okay. So this might be like k, depending on what your book, it's going to use different letters. So k equals 1 to n, and then a sub 1 r to the k minus 1. This minus 1 here is an artifact of the fact that we're starting our indexing with 1. And then it shows up here as I've got n terms. If you count this, there's really n terms here. Because it starts with r to the 0, then r to the 1. And if you start counting from r to the 0 and go up to n minus 1, that's really n terms. So that's a fairly natural way to think about it. You've really got n terms here, and then there's an n here. I usually think of it as whatever power you ended with of the ratio, you go to the next one, take that power, subtract 1, then you have to correct for this r minus 1 factor, and then put in the overall factor of a1. So if you write it in summation notation, that's going to be a way to write it. Okay. So let me copy that out separately, just those two, so it doesn't do weird things with yeah, okay. So for example, what would be the sum of this geometric sequence? Let's check that it looks actually geometric. 45 over 15 is indeed 3. 1 is 3. 135 over 45 is the same number, is 3. So it looks like we have r equals 3. So if we're trusting that this is not e, r equals 3. If we're trusting that it's geometric, r is 3. Okay. a1, I want that math mode, equals 15. Okay. And of course, we need to know n. Oh, and somehow I just totally deleted the 14 terms here. What the heck? This said 14 terms. Okay. And that means n equals 14. The number of terms really is the n. Okay. I'll put that in math mode, make it look prettier. Okay, so the sum is just going to be 15 times 3 to the 14 minus 1 over 3 minus 1. We can just evaluate that. Pretty big number, 35.9 million, roughly. But that kind of problem is fairly straightforward, and the only thing that's tricky is this n minus 1? If you talk about the number of terms, that's going to be n, and so that does go directly into here. Okay. What about this one? Okay. Here, r is going to be, well, it's the ratio 6 over 18, or 2 over 6, or 2/3 over 2, or 2/9 over 2/3. Okay. Looks like consistently the ratio here is 1/3. It's smaller than 1. So I'm adding up a bunch of things that get smaller. That's actually better in some senses, and we'll see it leads to very cool things when we try to make this an infinite sum. So r is 1/3 here, okay, and a1 is given. It's 18. Okay, and we got to figure out n. Okay, so we've got to match. We basically have to fill in the dot dot dots. We could explicitly fill in the dot dot dots. That's not incredibly hard, but let's do it a little more sophisticated way. Okay, we've got the sum 18 times 3 to the 0, sorry, 1/3 to the 0 plus 18 times 1/3 to the 1 plus 18 times 1/3 squared plus, and we want to write it as 18 times 1/3 to the n minus 1. We want to figure out what the n is. Okay, so we've got 18 times 1/3 to the n minus 1, and we want to match that with 2 over 729. Okay, so what we can do is just figure out, there's a 2 here, and let's just take the 2 out. Let me just do it in place. That's a 2 times 9, or a 2 times 3 squared. Aha. Okay, so the 2's cancel, and I get 1 over 3 to the n minus 1 with a 3 squared on top is 1 over 729. Now hopefully that really is, that 729 hopefully really is a power of 3, and that's where you actually have to figure that out. Turns out that's 1 over 3 to the 6. How would you know that? How would you figure that out? You could take the log base 3 of 729, and that would be 6. So maybe a log might have to show up here. Okay, so you really do need to know that that's 3 to the 6 if this is going to work at all. And one way to do that is to take the log. Okay, we're still not quite done. This guy on the left is 1 over 3 to the n minus 3. Oop, just kidding. Didn't have the 3 2 though. Okay, doing a little rules of exponents here. Actually, that might be a little confusing to do it that way. Let's do it as a third 3 to the power. 2 minus the quantity n minus 1. Or in other words, 3 to the 3 minus n. And then express the other side as a power of 3. I think that might be simpler. Okay. So what we've really done is we've taken that 1 over 729 and tried to express it without any fractions, but with a negative exponent. Okay, so now we get 3 minus n equals minus 6. And so n equals 9. Okay, so finally the n equals 9. This is a very typical thing. We're ready to plug into this formula. We've got this master formula. We're just itching to do it. And the hard thing is figuring out how many terms are missing. Okay, so now the sum is just going to be 18. Oops, not a fraction yet. 18 times fraction 1/3 to the 9. Right, so we figured out that this was really 18 times 1/3 to the 8th. You can check that if you want and really just discover that it really is 2 over 729. Okay, and it's the next power. We discovered that n was 9, so that n minus 1 is 8, but it's really n that shows up here. And then over 1/3 minus 1, then calculator's fine for that. You get a funky fraction over 729. What is the decimal for that? Very, very close to 27. That's interesting. 18 plus 6 is 24, plus 2 is 26, 26 and 2/3, and the claim is that it just gets super, super close to 27, but doesn't quite go over. That's going to be very suggestive for the future.